In this video, we will see how a Cartesian matrix distribution can reduce the amount of communication in the parallel sparse matrix vector multiplication. Until so far, in this computation, we have used a 1D processor numbering, but for Cartesian distributions, a 2D numbering is also convenient, and we identify then a processor ST in the two-dimensional numbering with a processor S plus T times M, where M is the number of processor rows, and this is a column-wise identification. And then we use whatever is more convenient in the circumstances. And if we have a Cartesian distribution, then phi ij depends on phi 0i, which is my processor row, and phi 1j, which is my processor column. And we can still concoct from this a one-dimensional number, phi 0i plus phi 1j times m, if we want to. Sometimes this translation is useful. Here we see a familiar matrix, Kh6, and this matrix has been distributed over 4 processors by a Cartesian distribution, a 2-by-2 distribution. You see on the left, you see the processor row, which is S, and S can be either 0 or 1, and you see the first part goes to 0, then 1, then 0 again, and then 1. And for the processor columns, we just use blocks, t equals 0 and then t equals 1. The nice thing about this is if you look at the matrix diagonal, all 4 processors have part of the diagonal. We start with yellow, then blue, then red, and then black. So the block size, of course, varies. And so the translation between a one-dimensional numbering and a two-dimensional numbering we also see in this picture. The red processor, for example, which is in processor row 0 and processor column 1, is translated to processor 2 in the one-dimensional numbering. We see there are many advantages to a Cartesian distribution. We've seen that already with LU decomposition. So it's row-wise operations. They are contained within a processor row, and similar for columns. And also, if you have an m by n Cartesian distribution, then the communication of vector component Vj in the fan-out is restricted to at most m processors. And similarly for the fan-in, also at most a number of processors, that's n, which may be a lot less than p. Another thing is that if we distribute the matrix in a Cartesian way, the parts that we get are submatrices. They are rectangular, so that's easy to think about. On the other hand, if we don't use a Cartesian distribution, the parts can have any shape. So these are all advantages why we would want to use a Cartesian distribution. Still, there's one major disadvantage, and that is that since we restrict the type of distribution, it may not be optimal. And so non-Cartesian distributions may still be the best. Here's a theorem. We have a matrix, and we assume that the matrix is distributed in a Cartesian form. So the distribution is given by phi 0 and phi 1, phi 0 for the matrix rows, phi 1 for the matrix columns. We assume that ui resides in one of the processors that has this row, which is processor row phi 0i. We assume a similar thing for Vj. Vj should reside in processor row phi 1j. A final assumption that we make in this theorem is that the distribution of u and v are the same. With all these assumptions, we see that the UI and VI, they are assigned to the same processor. They must be assigned to processor phi 0i, phi 1i. And that actually, by the Cartesian distribution, is the processor that holds the diagonal element aii of the matrix. And that gives a link. We see that the choice of a Cartesian matrix distribution determines the vector distribution, and vice versa, where then we need to fix m and n. So this is the link between the vectors and the matrix diagonal. They are distributed in the same way. And then we can do a cost analysis. Again, we need to make spreading assumptions. In this case, for the Cartesian distribution, we make additional assumptions. So not only that non-zeros and vector components are well spread, also the matrix rows and the matrix columns are well spread. And then, for example, looking at superstep 0, we see that we have n over p vector components, and they will be sent to at most m minus 1 other processors. So that's a lot less than p minus 1. And we can do a similar thing for superstep 2, and the others don't change that much. Now my question to you is, what would be a good choice of m and n? Well, the answer, if we add up all the supersteps, you see that the communication of superstep 0 and 2 gives a term m plus n minus 2 divided by p. And since m times n equals p, the number of processors, this is minimal if we choose m and n to be equal and equal to square root of p. And in this case, the communication term reduces to about 2 divided by square root p times n. And the other terms are not influenced by much, because we have a little bit of imbalance, n divided by square root p, but that's a lot less costly than the communication that we have. The number of supersteps doesn't change, and the first term, the main computation term, also doesn't change. So this minimizes our upper bound. Now we can use this also for dense matrices, because dense matrices, they are the limit of sparse matrices, where C goes to n, the number of non-zeros per row becomes n. And if we substitute C equals n into our formula, we see that we get a main term of 2n squared divided by p, which is really of an order of magnitude larger than the other terms. So we have lots of computation. Still, the communication then becomes 2 times n divided by square root p times g in approximation. So this is what we can achieve, but all the spreading assumptions must hold. So which distribution does give this? We have been extolling the virtues of the square cyclic distribution for linear algebra, for LU decomposition. But here, it doesn't work well. And the reason is that if we take the vectors and the matrix diagonal is assigned to diagonal processors P, S, S. And there are only square root P of them. So a limited number of processors gets the matrix diagonal. So also these processors are the ones that hold the vectors. So no good spreading of the vectors. So the diagonal processors have to send their n over square root p vector components to all the others in either a row or a column, so to square root p minus 1 others. So we still have a cost of about 2 times n times g. And that is not what we want. So we need to distribute the matrix diagonal across all processors. We could do that, for example, by taking the cyclic distribution of the rows by assigning, and of the vectors, by assigning phi ui equals I modulo p. We still have a choice then for the m and n. Now, let's assume that we take a cyclic row distribution. That means m equals p and n equals 1. So the complete rows are assigned to processors. This is an easy-to-use distribution, but it doesn't achieve our goals. It has the advantage that a complete row is assigned to a processor, so we don't need the fan-in and we don't need the addition of partial sums. We only have 2 supersteps then. But on the other hand, in the fan-out, the processor that has n over p components has to send it to all p minus 1 others. And again, we have about n times g as communication cost. We gained a factor of 2, but still, this is not enough. And here we have a distribution which does the job. If we choose a cyclic distribution of the vectors and of the main diagonal of the matrix, but we choose m to be equal to n, equal to square root p, then this does the job. And here we have an example. We have 4 processors, a 2 by 2 square distribution. The matrix diagonal, you see it's 0, 1, 2, 3, 0, 1, 2, 3. It's well spread across the processors. So you see the 4 processors here. And this achieves the goal. All vector components of a local processor, and that's n divided by p, they are sent only to square root p minus 1 others. Actually, in this case, only to 1 other. And that gets the communication down. So this is how you should distribute a dense matrix if you want to multiply it by a vector. A nice application of this is in artificial neural networks, which is part of machine learning. Here we see a layer of neurons on top, 8 neurons numbered from 0 to 7, and a layer at the bottom, also numbered from 0 to 7. And every neuron is connected to all neurons in the next layer. We have also distributed this computation, because we are performing a computation, over the processors, 4 processors, same colors as we've seen in the matrix. We can view the top layer as a vector v, because there we have strengths vj of the neurons. And the bottom layer also has strengths ui, and they are computed in this artificial neural network by adding the strength of the top layer with some weights and then performing another operation. So every connection has a weight, which in this case is aij. And these aij's, they are determined by the training of the neural network. So here we're talking about how we deploy the neural network. And then the computation of ui, so that's the new strength, or the strength in the bottom layer, is a function of the sum of aij vj plus bi. So the bi, it's called a bias. B is a bias vector, and bi is the bias of the ith neuron. So that's added to the result of a local sparse matrix vector multiplication. and then a function is carried out on the result. And this is a nonlinear function. And the simplest one is just taking the maximum of 0 and x, which is called the ReLU function, the rectified linear unit. And this looks very much like a sparse matrix vector multiplication, or a dense one in this case. And by assigning the neurons and the weights to processors in the way that we did for the matrix, we minimize communication here as well. Another way of doing it would be to slightly change our distribution. We still have a spreading of the matrix diagonal, but now by the block distribution. So we use blocks also for the vectors. And for the rest, this one will work as well. And we can translate that also for our neural network. And then we get this picture. Now there's a bit more locality in the picture. You can easily see that, for example, neurons 0 and 1, they're the connections to the next layer. Some of those connections, they are yellow, and the neurons are yellow. And so there's no communication needed. Only for connections to other processors you need to communicate. So this works well, equally well as the previous one. But if you're limiting the number of connections, not all to all, but for example only to neighboring processors, then there's some locality, then the block distribution might work better. To summarize, we have a Cartesian distribution, we can use that, and then we either use a one-dimensional or a two-dimensional numbering of the processors. We have seen how to distribute a dense matrix for multiplication with a vector. We use a cyclic distribution or a block distribution of the main diagonal and distribute the vectors in the same way, and that works very well. We can use this for the artificial neural network. A final question. Here we have another artificial neural network, a convolutional neural network, where every neuron is connected to only the neighboring neurons and to it in the next layer, and of course to itself, but then in the next layer. And this is a number of neurons that's large, so larger than actually in the picture. Assume that we have that, and that we have a parallel computer with P processors. How would you distribute the neurons and their weights? How would you assign them to processors?